Let's get going with the first part of the program. This will be a presentation by Professor Karsten Berns from the TU Kaiserslautern on autonomous construction vehicles. Nina Heide is going to moderate this part of the workshop.
Hello and a happy welcome also from my side. And we are very happy to have Professor Karsten Berns here for our first invited talk. He's a professor at the University of Kaiserslautern and the head of the Robotics Research Lab. And he received his PhD from the University of Karlsruhe, so very close to our Fraunhofer Institute. His present research activities are the realization of reliable complex autonomous robotic systems. And in this regard, he and his research group are developing a robotic middleware, a behavior-based control architecture, and also different validation and verification methodologies. The main application area here is off-road robotics. And in this, the autonomous and semi-autonomous vehicles like small trucks, excavators, or also tractors. Professor Berns is the spokesperson also of the Center for the Commercial Vehicle Technology at the University of Kaiserslautern and the leader of the Technical Committee for Robotic Systems in the Gesellschaft für Informatik. So we are very happy that we could win him here as a keynote speaker today. And Professor Berns, the stage is yours.
Thank you very much for the kind introduction and also for the invitation to this workshop. Today, I expect I have about 25 minutes. I'd like to present a little bit our work in the range of construction vehicles. I would like to focus a little bit on some ideas how we can structure an unknown environment which is later on used for navigation tasks. So first of all, a short introduction to my group. You see here more or less in the area of vehicles, of autonomous vehicles, different application areas in which we are active since the last years. I will point out this area of construction machines. Beside this, we have also developed several test vehicles. Like Raven is a very famous one because we start here in 2006 with this machine and were driving in forest environment, get a lot of experience how we can control such vehicles. And from these days on, we look for a lot of other applications together also with industry to build up powerful machines which in an autonomous way or in a semi-autonomous way can navigate in rough terrain. We are a little bit involved in agriculture vehicles since the last year and have some projects, as you see, also in the range of rescue vehicles. Let's come back to the construction. And I have here more or less an overview of things what in modern construction should be solved. You see more or less how people see the construction site of the future. So in this, we have, of course, a lot of interaction from the cloud, from different actors which like to interact with the construction site, get data or control the vehicles, deliver new tasks, get information which can be handled to find out if the planning is or the planning process, what is done is correct at the moment, and so on. So if you look for the middle, you have, of course, the things what we like to support. This is more or less the construction machines. They must be at least semi-autonomous. Otherwise, you will not have a nice production or construction in future. But also you should have on this construction site additional installed sensors. It's not only on the machines, but also we have cameras or other sensors in the construction site itself, which can also be used by the machines to operate in a correct way to get additional information and so on. So this is more or less the scenario in which we are normally are. And of course, you can ask, why do we need in construction now more intelligent machines which can do a lot of operation by itself. And the reason is here more or less listed. We'd like to have in future a much higher quality of the construction process. Everyone knows, even someone who has built a house, how the quality is very often, how low the quality very often is, and how many problems arise because normally manual production is not done in a correct way. Then we like to have, of course, a much higher efficiency. Think about the huge amount of houses which we like to build in future. There are, of course, countries like China which like to build in a small region more than 1 million houses in a short period of time. So even here we have to have a much higher efficiency as today, and we hope, of course, with such machines we can reach this. On the other hand side, we like to reduce the resource costs like CO2, energy, and so on. So this is also a very important thing, even in our discussion here in Europe about the CO2 pollution, that we have other techniques where we can reduce this. Of course, also on the other hand side, we have to be absolutely safe, even in construction. We have a lot of accidents up to now, and this should also be better in future with autonomous or semi-autonomous machines where no one will be in the machines or around the machines. And last but not least, this is also a very important aspect if you talk with industry. We have here, even in Europe, but especially in Germany, a lack of manpower. So we have discussed with big construction companies which says, if this goes ahead in this way, we will not produce any house in the next 10 years because we have no one who built this house. So also we have to take this into account. And of course, we see one solution in the development of autonomous construction machine. On the right-hand side, you see a few machines. I have not listed here too much the state of the art. What is existing, these are prototype machines. You find also a few very simple machines which you can really buy. But here the ideas, you see a few ideas, concrete surface finishing or brick placements. There were several machines built in the past. The tiling machine, shotcrete technology, or panel installation. These are typical robotic systems where you like to have a mobile machine, but also with an arm, with something which manipulates in the construction environment. The questions which rise, if you look for such type of applications, as we have seen it on the last slide, is how should we build such construction machine in future? And it's clear if you have no human in the loop, maybe outside in a monitoring center, but not on the machine itself, you need no cabin. So you can also produce from the mechanical point of view, from the design point of view, the machines in a totally other way as today. And you see here two examples. One was by Volvo, this mobile cart. So this is of course a truck, but as you see, a totally different structure of a truck. And we were involved in this development of this Omag roller, which is also not having any cabin and is also driving in an autonomous manner. We also can ask about the mechatronics concepts and the embedded systems. So how can we develop such concepts so that also industry can buy this at the end? So of course, if you look for our prototype machines, they are very often very, very expensive. So this is not a market. So we have to reduce the cost of both of the embedded system, of the control system, but also on the sensor system. At the moment, these prototypes, of course, cannot be sold on the market because the price would be too high. Very important, I will say a few words later on, is the digital twin, which is used for testing, but also for generating of training data. what I think is extremely important if you like to go in this direction and develop such machines. The control architecture will also say a few words about our control architecture, control concept, the environment perception. These are all questions what is needed. My personal view is that we will see much earlier such machines from the autonomous way, acting on the construction side or in a semi-autonomous way, because on a construction side you have one advantage, that we very often have a private area, so specific rules which are normally in the public area are not so hard in the private areas. There are also rules. So the idea, as I said, is with our research to look how we can, in a very unstructured environment, control very slow moving vehicles. And of course, guarantee of safety is also an issue which we have to consider. So simulation, why is simulation for us so important? And you see, maybe I can also run, hopefully the video can be seen. These videos in parallel. We like to have simulation because it's impossible to test in a rough outdoor environment. You see here in a natural environment, but also on a street environment, our controllers, our perception system in an adequate way, because you cannot go infinite out with your machine and test this. This is impossible. And everyone who has real machines and go out, you know that we can test only a little bit if we go out. And even if we are a longer time out, what we really can test is nearly nothing. And what, for example, if you think about the perception is important, if the light condition change, if the shadow change, we have, of course, totally different behaviors of the percepts. And we like to find out if even under these conditions, the system will work. On the other hand side, we are also interested to use, as all people in the perception area, such deep learning networks where we have to generate training data. And even we know that this is very hard to generate the training data. So we also have worked on here together with this Unreal Engine to generate directly out of such simulation training data, which we have, of course, not to tech. So we can directly make this in an automatic way. For example, persons running around under specific conditions. We can also make snow or other light conditions or dust even, and test what the sender quality is. So this hopefully in future will help us tremendously. We have very nice first results where we can test this or generate this training data. Testing, as I said, is an extremely important thing. How can we really test our machines also to be safe with the machines? So if something goes wrong, we have very expensive machines, we will destroy the machines also. Before we test on a real machine, we should be sure that the algorithm is roughly working. Therefore, we use here this Unreal game engine. We have extended it a little bit by us. It offers also a little bit physics. The physics is not a perfect physics as other tools, but it's enough. It's an online tool, so everything what you see is really what happens if you make the test. So you have an online observation. You get also, say, 30, 40 images per second, which you can process with your algorithm. We simulate all our sensors, which we have on the real machine, so that we can make the same processing as on the real machine. We have a lot of environments in the meantime where we have different construction, but also agricultural environments and so on, where we easily can test and change the conditions. So that's why we think without such a tool, a very powerful tool, you cannot solve these problems what I have listed before. Coming to the control, and I like shortly introduce more or less our concept, how we control our vehicles. We have a so-called behavior-based control concepts and implement years ago our own behavior-based language, which is called IB2C. We have also a middleware that is called Finrock, which we use. We use not WhatsApp middleware. So both, of course, is working together, but I only like to show you here the behavior-based concept. So the idea how we implement the percepts, so the units, the module which recognize the environment, or the controllers which are on a low-level control but also on high-level control, are these modules which you see on the right side. The behavior model is first of all totally free what we put in. So this can be very, very complex. This can be a neural network. This can be a very simple function which is included. So we say nothing what is really inside this behavior box. And we do this because, of course, we also have to use standard algorithms which we find in internet, and we use it. That's why we are totally open what is going in. The most important thing are the meta signals, S, I, A, and R. And these meta signals are used more or less to build networks and to fuse information. This information is, of course, a stimulus and inhibition. On the other hand side, A and R stands for the activity. Activity means how strong should this behavior participate in the overall behavior of the system. And R is a kind of self-reflection. So we like to say how far I'm away from the internal target of the behavior. And this is also helping for the fusion and for also building these big networks. You see our fusion node, we have average fusion and the maximum fusion, what we normally can do. Also, this is influenced by the parameters here. And based on this, we get, of course, a mixture of control values, for example, or weighted by the activity, or we select the maximum based on the maximum activity, the control value. Same can be done with the percept. The percept node is a little bit extended. You see this by more or less, you have D is the data, by a standard derivation, what we expect from the data, and here the target derivation, what we can accept from the application point of view. Later on I can show you quickly, and we calculate also a relative quality. And why do we do this? This gives us information. For example, think about a distance sensor, and suppose you have a derivation of plus minus 20 centimeter. We cannot say based on this how good this is for our application. We have to look for the application itself. If, for example, the control must not be too precise. If 1 meter is enough, this sensor is perfect. So this derivation is not bad. If you said we like to navigate in centimeter dimension, this derivation is, of course, terrible. So we like to consider this derivation according to the application itself and calculate based on this a kind of confidence value, how confidence is, for example, this perception. And this is what we later on use. So here, over this IB2C, we have now developed our reaction architecture. This is also used in all of our robots. And this has more or less a similar structure as all these control architectures, what we see in other robotic systems. We have, of course, here this typical control part, the red ones. We have the perception part. These are the yellow ones, where also information from a database can go in, or knowledge can go in. We have then an abstraction layer, which can then be used to control the simulation and the real machine. So all our algorithms can switch or run this in parallel, doesn't matter. So we can directly go to the real machine, to the simulated machine, or as I said, we can also run both together. So this is the concept what we have. And I now like to say a few words about our Unimog. This is a typical transportation system for rough terrain. You can use it on construction site, but also in forest application or in agricultural application. And we have developed this machine in the last 4 years. We put a lot of sensor on it. You see a lot of laser scanner on it, but also stereo camera system. And of course, inclination sensor and so on, and GPS and whatever is on such machine, but it's not so important at the moment. So what we have to do to drive this vehicle in very rough terrain is to control the high degree of freedom of this vehicle. And this is not easy because you can control a lot in such an Unimog. And you see here on the left-hand side, this differential lock, what you can control, gearbox, tire pressure, frame bend, 60 centimeters. This is very important for going on rough terrain. Articulation, which has maximum 30 degree. And we have a portal axis, a ground clearance at least of 50 centimeter and so on. So we can control a lot of parameters depending on what we recognize from the environment. And now the question is, how can we control this and how can we more or less percept the environment in such a construction areas site in a correct way. And now I come back to more or less this perception node, how we do this. You see here now the measurements of these different laser scanners. Here only the laser scanners are shown. But all these laser scanners which we have put on the machine have, of course, first of all, different areas where they normally measure, but there are also overlapping areas. The main problem is that we, in this overlapping area, have different quality of measurement. So even in this laser scanner, we have really different qualities. This is the precision. This is, for example, the distance where more or less later on the measurement will be not so perfect and so on. So we model more or less this with typical the diameter of the beam itself, the distribution where we measure min-max range, what we measure. And this more or less goes in the model to calculate at the end the confidence of each of the measurement in the cells. So we structure the environment around the vehicle in voxels, and then we describe more or less the confidence of all these measurements according to the quality of the sensor itself. So, and what can we do now with it? This is another aspect. We have to get rid of a lot of disturbances. For example, when we go here on such a construction site area, we generate a lot of dust, and this can also lead to some problems. You see this here, and we have to get rid of it. We do a lot of experiments, how we get rid of it. The last is not finished work is done with a master thesis where we like to train a neural network to reduce more or less the dust here out of this 3D measurement from the laser scan. If you see the stereo point cloud, maybe I speed a little bit up, you see that even the quality of this measurement is not comparable with laser. Of course, we know this. And we know also that the far distance, you see this here, the sigma point cloud, sigma is what we have in our behavior nodes, is getting worse and worse. Here, the colors are, if you are blue or green, this is okay from the confidence of the measurement. If it goes to red or even to brown values, and it's getting more and more terrible. And we can now use this for the fusion process. And you see, I don't go into detail of this hash-based algorithms, the O from N algorithm. But what we do is we estimate more or less the confidence based on these ideas from the data sheet, and then extract in overlapping, when we have in voxel overlapping measurements from different sensors, we extract one measurement which have the best confident value. So we reduce the basic measurement by a lot of points and generate but high confident values. And you see this here on this example. For example, these are here the yellow ones with not very confident. This is the yellow, comes from stereo image processing. The blue, which is very confident, comes from stereo processing. And now we have a situation where we have an overlapping field, and now we can make the trick. If we have in a voxel only, for example, stereo point, we have to use it. But if we also find a laser point, we will replace this by the laser point. And so this is how we can now build, on one hand side, a nice 3D measurement of the surrounding. On the other hand side, we have to every measurement a confident value. And this confidence value can now used for the control. We have a video. I think I have no time to show this, but later on, if you go under YouTube, we will have also the video under YouTube. You see the same experiments again. So now we can check more or less based on this confidence value. Here you see the quality view. What is more or less safe from the measurement and what is very risky. And you see here, in this case, this is very risky. The last part, the blue part, is where we can try. And based on this, we can now use this for the control. Not only that we get measurement, but also we get the confidence value for the measurements. From these units which we measure, we can then make a semantic segmentation. This is also what we have done. We can now easily extract more or less boxes where objects are and classify these boxes and to features, to semantic features. And these semantic features can now be used for, I skipped this a little bit, run out of time, for more or less describing ontologies. So we have defined rules where we in addition can say something if a combination of features appear that it's more risky or not. Maybe I give you an example of this idea, a very simple simulation where we said here ahead of the vehicle we recognize two pedestrians, and now we can add this and said, yeah, if a pedestrian is coming, we don't know how the pedestrian behaves. So this could be a more risky situation as at the same position, for example, an object is measured. So we, for example, can use such a rule for reducing the speed in a much earlier way. Otherwise, normally we go ahead and then in a near range we will brake. But we can, of course, do this now another way. Another example, what we have done, we said if the situation is wet and I have on the right or left-hand side of the pathway a meadow, we will not drive too hard on the meadow because we can slip away. So we will have a different behavior if we have a wet situation as if we have a normal situation, and this comes out of rules. So we couple what we recognize and where we calculate some values out of our behaviors with information which comes from the database, which also influence the control itself, and both together gives them the reaction. I skipped this, as I said, have a look for this experiment. We have this under YouTube. You can start this directly. If you go YouTube RR Lab, you will see this. Maybe at the end, three other examples where we have worked on in the last year. So we stopped at the end of last year. This was drum roller. So here it was important to navigate a fleet of the drum roller behind this production machine. And here we can also add more drum rollers and reduce drum rollers. Important is that you see this on the first video, that we have to cover that in a specific time range. We can only move over it and compress the concrete or whatever this is. Could be Tumen. If you run out of time, the operation is useless. So you have to guarantee, you make a plan that you coordinate the machines in the right manner so that this is possible. Let's have a look to our excavator. We have also over last year's excavator projects with Volvo, with John Deere. We have an excavator now in our group. And here it's automatic digging, which is important. We recognize here if we have a trench, for example, which we like to dig the environment, we like to recognize the situation. We measure how easy it is to move through the sand or whatever you have, and then also decide to change the trajectory. What is also important is later on, if you have a bigger site where you like to get rid of the sand, from where do you dig? And here we have also make a concept that automatically we know where to take what out of the earth to get at the end a fixed construction. Last but not least, this was more or less another project what we have with a mobile crane. Here, safety aspect was very important because we have now here cameras on the top of this mobile crane, so up to 40, 50 meter. And we like to identify, of course, people under the load, which can be very, very risky. And automatically, then this crane should stop. Was hard, this problem. We make experiments with different neural networks because you see not too much from the people here from the top. It's much easier if you see the people from the front to make the classification. But at the end, also with the SUUE system, we were able to manage this in a reliable way that we really detect and separate people from other objects which look in a similar way. So I think I have to stop. So thank you very much for your attention. And if you have questions, please ask.
At first, very much thank you for your interesting insight and your work on autonomous construction machines. And we have one question from the chat. So I think I'm just going to read it out for everyone. The question: difference in the ranges of LiDAR point clouds and those obtained from stereo, because the overlap of the point clouds from the LiDAR and the stereo is not always given at larger distances.
Yeah, you are right. So of course, where we have an overlap, this is in the near distance. So our stereo system, what we use here in this test with the Unimog, has a maximum distance of 20 meter. And of course, only in this area, we have an overlap with laser data. If you go over it, you have only the laser data. But we move over time. So this is for more or less driving in such an environment. So you will see after a while, of course, also with the stereo camera system, this point, this distance point. And then, of course, you have to do the same operation as I have explained.
Okay, do we have other questions from the audience via the chat or also directly here? I do not see any raised hands, so maybe I also have a question concerning the confidence analysis that you showed. Now, from your experience, we are also working, of course, with LiDAR and stereo cameras. What's more or less the range where the stereo point clouds cannot contribute anymore from the confidence measurement side to just add up to the LiDAR measurements for the environment perception?
Yeah, this is of course the stereo model and depends on the cameras itself, on the resolution of the camera itself, as well as the stereo base itself. Of course, if you go with the stereo base, make it broader, you can measure in a longer distance. But of course, in the near distance, you will not get nice data. Of course, this depends on it. And of course, you should have a lot of pixels. If the number of pixels is too low, you get, of course, very soon a problem. So these are more or less influencing this. And of course, the quality of the camera. This is also very important. You have very nice, from the optical point of view, very nice cameras. And you have cheap cameras where the optic is not so good. And this also influences a little bit the quality where the reliability is coming.
Okay. Thank you very much. Peter, do we have time for one more question? There is one in the chat. Or
I think that's possible. We're going to move a bit into the coffee break then.
Okay.
That should be okay.
The last question was, may I know how the sigma point cloud is estimated?
Yes, as I said, the sigma point cloud, this is just this, I show it in a very short manner, this percept node and the parameter in the percept node. Here we take into account everything what we know on the low level. If we consider raw data from a sensor, the data sheet of this sensor itself. And based on the errors which are described, the derivation, we generate the sigma. And this big sigma was more or less the value which is allowed from the application point of view. But we show the small sigma here in this diagram. And based on the sigma, you can make a threshold. You can say, okay, if this is too bad, we cannot use it. So throw it away. So we cannot use such measurement. This is just what we are doing. Of course, you can then measure again or drive to another position to get a better measurement. So you have a lot of options what you can do. But in general, come back to the question, the sigma comes from the data sheet itself, from the error and the derivation of the measurement principle. This is what we take into account.
Okay. I think that also answers the question in the chat very well. Thank you again. And so I think we move to our next talk.